Okay, welcome back. A couple of announcements. Uh, so I have completed all the materials for this course. So even for tomorrow, I have uploaded the materials. So I have finalized the topics for tomorrow. So I guess so this morning we'll be talking about non-bipartite matching and the matching polytope. So this will be the end of the story for the matching problem. And in the afternoon, we're gonna talk about something called submodular function optimization. So I was scheduling a couple of lectures, like 3 or 4, to discuss this topic. But I just realized that I can cut down um, some stuff a little bit, and so I will have one. So we will have one lecture on submodular minimization and its application in something called chance constrained programming, which is a kind of stochastic programming problems. And we'll also talk about submodular function maximization, which has quite a different story from submodular function minimization. And I'll discuss two algorithms like simple greedy algorithm and continuous like Frank-Wolf type algorithm for solving continuous problem. Okay, and tomorrow we'll have two lectures. So in the morning, I'll discuss the like black box optimization, not just in the combinatorial context, but it can be applied to continuous problem as well. And the last lecture will be about my recent research. And I was working on, I was, I, ha- so I have been working a lot on like reinforcement learning theory. So that's like multi-arm bandit and regret minimization. And I'll discuss some of my recent results with my students and my colleagues. Okay. Okay. Even the reinforcement learning problems, this kind of theory can be related to combinatorial problems. I hope that you guys enjoy it. Okay. Okay. So, any questions? All right. So then, let's continue. So today, so far we have discussed lots of materials for the bipartite matching problem, where you assume that your graph is bipartite, but not all graphs are bipartite. In particular, you could have some odd cycles, then you get some more complex situations. For those graphs, we can still solve the matching problem, and that's called non-bipartite matching. I'm gonna present Edmonds Blossom algorithm, and the algorithm is a simple modification of the augmenting path algorithm. And in fact, the augmenting path algorithm was part of Edmonds Blossom algorithm. Okay, and I'll discuss that, and I'll talk a little bit about something called polyhedral theory. And polyhedral theory, I guess we discussed a little bit about polyhedral theory, although I didn't mention its name for the last 3 days. But I'll formalize what we talked about, especially in the context of solving linear programming and integer linear programming. I'll lay down the foundations for that, and I'll explain that any integer programming problems can be reduced to linear programming, but I'm not talking about like complexity perspective. Okay, so that's what we're gonna discuss. Okay, so non-bipartite matching. So we talked about, so today we'll discuss graphs that are not necessarily bipartite. Okay. So, we say that a graph is bipartite if and only if there's no odd cycle in there. So you could potentially have odd cycles like in this picture, right? So I have a triangle and I have a pentagon right there. And if you look at this graph, I'm interested in the maximum size of a matching. and the minimum size of a vertex cover. Now, if you look at this graph, so we can take at most one edge for the matching, but you need at least two vertices to cover all these edges. So the minimum size of a vertex cover is 2, but the maximum size of a matching is 1. For this 5 cycle, we can take at most 2 edges, but you need to take at least 3 vertices to cover all the edges. So in these odd cycles, the minimum vertex cover has more vertices than the number of edges in a matching. Okay, that means that Koenig's theorem doesn't hold. In general, if you take an odd cycle of length 2k plus 1, then you can prove that the maximum size of a matching is k, whereas the minimum size of a vertex cover is k plus 1. Okay. That was not the case for bipartite graphs where these two numbers coincide. Okay. So Koenig's theorem doesn't hold, and we see a gap between these two numbers. And why is that happening? Well, I guess we observe this, and let me get back to these non-bipartite matching problems. Now, I'm interested in computing a maximum matching for a non-bipartite graph. So the first naive approach is to take the augmenting path algorithm and just run it. And perhaps, as our observation says that, the Koenig's theorem doesn't hold, maybe it's probable that the augmenting path algorithm doesn't do its function. So, but what is the outcome? Okay. So let's look at the example here. So we have a non-bipartite graph. We have a bipartite graph on the left, and I have added this h between u and v. And you see that there's an odd cycle of length 5. So the graph on the right is not bipartite. Okay, but I have the same picture except for this h between u and v. So I take this m exposed vertex r, and I apply the augmenting path algorithm, so the alternating tree procedure. Okay, so if you run the same algorithm, in fact, you get the same alternating tree from R. Okay, you start from this vertex R and take its neighbor, and the neighbor is matched. So you add this matching edge, and you have this vertex at the even level. You enumerate all the neighbors, and you realize that the neighbors are matched. So you also enumerate the edges, and you are done. So U and V are at even levels, but they are not adjacent to any other vertices. Okay, so that's done. You apply the same procedure on the left, on the right, and you still get the same tree. Okay, except that you realize that there's an edge between U and V. Okay, but the alternating tree procedure doesn't do anything, even on the right. So what you do is, I have found my tree and I cannot grow it. So let me take out all the vertices from the tree. Okay? What you have after that is these two vertices x and y, and also x and y on the right. And they become isolated, meaning they are not adjacent to any vertex. If you remove all this tree, then the augmenting path algorithm says, there's no augmenting path, m augmenting path, and conclude that the current matching is maximum. Okay, that's what the algorithm does. Well, but is that right for the non-bipartite graph? Is there even maybe for the bipartite graph that is correct, right? We proved this correctness of the algorithm. But is it correct that this non-bipartite graph doesn't have a augmenting path? Is it correct? Is there an augmenting path then? That's right. So, that's great. So there's an augmenting path from, so x and y are, two exposed vertices. So you can take a path from x and y, and that's it. That's M augmenting. Okay. But in fact, I want to use this starting vertex R, okay, which is exposed. So even starting with this vertex R, you can find an augmenting path. So in fact, you can take a path from R to X, which goes around the cycle using UV. That's important because without UV, we knew that there's no augmenting path. Somehow you need to use UV this way. Then there's a path between R and X, and that's augmenting. Okay. So, but the problem again is that the augmenting path algorithm with the current alternating trees procedure cannot detect any difference between these two pictures. Okay, that is the first issue. The second issue, well, I guess it's similar, but I'm gonna explain which part in the analysis fails for non-bipartite graphs. Okay, so if you remember the proof of Koenig's theorem or the analysis of augmenting path algorithm, so we drew this tree structure. Okay, so so this is the maximal alternating tree from this exposed vertex R. Then you can take vertices from the even levels and vertices from the odd levels, and odd level vertices will go to U, and even level vertices will go to W. Okay, and the key component we argued for bipartite graphs was that if you look at two vertices from even levels, there's no two vertices that are adjacent. In particular, if you take U and V, there's no edge between U and V. There was a key component, key part to argue that you get a maximum matching and a minimum vertex cover, right? But but if you have an edge between, so in this picture, so U and V, these are two vertices from an even level. There can be they can be adjacent if your graph is non-bipartite, okay? Because it could have an odd cycle. In that case, there are two adjacent vertices from the bottom. So this is the part where the proof and analysis fail. Okay. Uh, Great. Any question? Okay. So augmenting path algorithm doesn't work for non-bipartite graphs because of this picture. And what I worry about is, in fact, you could also have edges between these two. Okay, let me draw. And this also creates an odd cycle. So even a edge between two odd level vertices, as long as they are at the same parity level, you get an odd cycle. But what I care about is an edge between two even level vertices. Okay, that's where the analysis is important for bipartite graphs. Okay, so that's what I care about. So here's a fix due to Jack Edmonds. Okay, by the way, Jack Edmonds is still alive. Surprisingly, and I met him when I was a graduate student. I guess it was 8 years ago. And I was the youngest person, and he was the oldest person. So I guess the conference venue was awarding a nice little T-shirt to Jack Edmond and myself. I guess I was looking for a picture take with him, but in fact I somehow I deleted the picture. I have a picture with I got a I still had a picture with the organizer, but not with Jack Edmonds. But he's a okay. Yes, it's being recorded, so I can say. Yes. He's an interesting figure. I mean, but it was quite inspiring to, I guess, talk to a person who's very very famous and who has pioneered all this work. Anyways, so here's a very nice idea by Jack Edmonds. So every time you find an edge between two even level vertices, I only care about even level vertices. Okay, then we find a knot cycle, and this is called blossom. Okay, blossom, and it always the search always starts from a exposed vertex, and it goes to somewhere. Okay, somehow when you create an odd cycle, it looks like a flower. If you, I guess, reverse the structure, um, R looks like a root, and starting from a root, you grow a stem, and there's a kind of a blossom or like kind of thing. And this entire structure with the from R to this cycle C is called a flower, and this odd cycle is called blossom, and this path from R to the cycle C is called a stem. Okay, so this fancy name in graph theory. Anyways, so whenever you detect this odd cycle, what you do is you contract the vertices. Okay, so you contract the vertices, and then you define a single vertex to replace all these things. Now, what happens to the vertices x and y that are adjacent to one vertex in this cycle? You connect these two vertices to this vertex that corresponds to the blossom. Okay, this is the idea. Okay, great. Then I can forget about this edge between these two even vertices. Then the question is, can I does interesting structure of the alternating path and alternating tree, does that preserve after contraction? And in fact, that is the main, I guess, analysis tool. So let's say I have a graph that is not necessarily bipartite, and I have a matching, and you take a blossom, and what you do is you take, so there's an augmenting path in this original graph, if and only if there's an augmenting path in the contracted graph. Okay, what it means is if your current matching is not maximum, then you contract and then you find a knot cycle and you contract it, then the matching after contraction is not maximum. You can improve it. Okay. Now you work over the contracted graph, and because this is not maximum, you can find an augmenting path. Then you can reconstruct an augmenting path in the original graph. Okay, so this proof, although the statement doesn't say that, but that's what we can do. So in the algorithm sense, we grow a tree, and if you find a blossom, you contract it. Okay, then we look at a smaller graph, and then we start searching again. And if you find an augmenting path, then you can reconstruct an augmenting path from the original graph. That is how it works, and you improve your matching, and you do that. You repeat this procedure. Okay. Any question? So this is pretty much it for non-bipartite graphs, and the other things are the same as the bipartite case. Yeah, I was talking to some students last night, and we were talking about like how efficient the ChatGPT system is nowadays, and I realized that somehow if you you can draw a picture like this using ChatGPT, but I was working really hard on making this figure. Like I was thinking about like how to deliver the idea in a clear example, but somehow like you can draw this with ChatGPT, just typing some, I guess, comments, but I don't know how to do it. So I just drew it myself. Okay, what this picture says is the following. So let's prove the first direction. So let's assume that there's an M augmenting path, okay, which is okay, reconstructing on M augmenting path. Okay, let's prove that there's an okay M. So there's an augmenting path from the contracted graph. Okay, let's argue that. Yeah, let's assume that, which is the top path. Okay, so let's say the vertex C is part of the augmenting path, and I want to create or reconstruct an augmenting path in the original graph. That's what I'm gonna do. Okay. So suppose that C is in the middle, then it's connected to a matching edge and a non-matching edge in the contracted graph. Okay. Now let's uh but there's a matching edge. But if you look at this blossom, if you just look at the vertices in the blossom, there's a single vertex that is not covered by matching edges. Okay, if you look at these two edges, they are part of matching. Well, you have this single vertex U that is not part of the matching edges. That's because a blossom is an odd cycle. Okay, so that this matching edge before contraction has to be connected to this vertex U that was not covered by a matching edge inside this odd cycle. Okay, and the other part of the path will be connected to an odd level or an even level. Okay, let's look at the case where the other part is connected to the even level. Then I can claim that I can prove that there's you can find an augmenting path. So that's basically you go from x to u, and you take this path, and that gives you an augmenting path in the original graph. Okay. What about the case when the second part is connected to an odd level vertex? What you do is you take this route and go u to u and x. And this gives you an augmenting path in the original graph. Okay. I'm explaining this in picture, but this is based on the structure of this blossom, where except for one vertex, all the vertices are covered by the matching edges, and it has an odd length. So an odd cycle, and it consists of two alternating paths with different parity. So no matter where this vertex V is located, you can complete the picture to create an alternating path in the original graph. That's the idea. Okay. Question? Now the other direction is a little bit more trickier. Okay. So I'm gonna assume that there's an augmenting path in the original graph, and I'll argue that there's an augmenting path in the contracted graph. This is the converse direction. Okay, that's what I'm gonna do. So, but I'm going to do some trick. So let's say that there's an so because we have spotted a blossom, there's an exposed vertex R, and there's an alternating path. Before we detect the blossom. Okay, so this is M. To avoid some issues, what I'm going to do is I'm going to take another matching. Okay, I'm going to take matching M prime. So this vertex is U. So U is the, I guess, branch vertex of the stem of the blossom. So which is the unique uncovered vertex inside the blossom. Well, in fact, this can be covered by another matching edge outside the blossom, but we have this branch vertex U. So let P be the stem, which is the RU path in the alternating tree. Tree from R. So I'm going to take the stem. Okay. And you know, U has to be on even level vertex. Okay. So the length of this path or the stem has to be even. So it has to start with a non-matching edge and matching edge, and it has to end with a matching edge. Okay. So I'm going to define let another matching M prime to be a symmetric difference of my original matching and this path P. Okay. So what I do is for the edges on the stem, I'm gonna change the status of matching and non-matching. So after this, you're gonna get this picture. So I have this. So for the blossom, I get the same. But now R becomes uh, covered, but U becomes uncovered. Okay. Now, this edge, there was this matching edge attached to vertex U was the unique matching edge covering this vertex U. But now I took it out in my new matching. So now U becomes exposed, but whereas R becomes covered. So this is my new matching M prime. So because we assume that as there is on M C augmenting path, we know that M set minus C is not maximum matching. So M prime, we just change the status of the edges on the stem. And so M prime has the same number of edges as M. So it means that M prime Z minus C is not maximum matching. Just because M and M prime have the same number of edges. So that means that there's an M prime C augmenting path. there can be an augmenting path using this new matching. If it's not going through uh, this vertex C, then we are good because after contraction or anything, it doesn't go through any vertex in C. So there, the same augmenting path will remain in the graph without any changes because I'm only contracting the vertices in the cycle. If your if your path is disjoint from this blossom, then the same augmenting path will remain even after this contraction operation. So the only case that I need to worry about is that the augmenting path go through this some vertex in C. Okay. But then you can argue that we know that this vertex is exposed because that's the way we designed this new matching. We took these edges of the stem and we make this vertex U uncovered, exposed. So if there's some augmenting path that go through this cycle C, then you should find an augmenting path from U to an exposed vertex like this. Okay. Let me leave it at this point. Okay, if you argue, think about it a little bit more, then this will be clear. Now, once you argue that if you find an augmenting path from this exposed vertex U to another exposed vertex Y, then let's contract this blossom. Then if you contract this blossom, C is also exposed, right? Because, before contraction, this was the unique edge that was outside this blossom that is also part of a matching. But then if you change the matching, then we just remove we made that edge not part of the matching. So now if you contract the thing, there's no matching edge that's incident to this vertex C. So C is exposed. Now I have this exposed vertex. So this gives you an augmenting path in my new matching. Okay, so this proves that M prime C is not maximum, not a maximum matching. And also this proves that MC is not a maximum matching. There were some subtle points when you argue all these cases. So if you go through my lecture note, or if you try to reconstruct your own proof, the only case, the case you need to worry about is when certain augmenting path intersects some vertices in this cycle or the blossom. But like the locations of this, you could also have augmenting paths that go through something like this. You enter into this vertex V and leave here. You can kind of create some weird cases. But the argument is that even with this case, when it doesn't go through this vertex U, you can redirect your path so that it goes through this vertex U, and you can control the situation so that after the contraction, you can create this picture. There are some other points inside the proof, but I recommend that you, I guess, rediscover what I found by yourself. Okay, but the main component of the ideas is here. Any question? Okay, let's talk a bit about, okay, let's summarize what we've done. So here's the modification of the augmenting path algorithm, taking into account a blossom or a not cycle. So we have a matching and we find the exposed vertex. If there's no exposed vertex, it means that my matching is perfect. So it's automatically a maximum matching. So you should be able to find an exposed vertex unless it's perfect. Then starting with that exposed vertex, you grow your alternating tree. Okay. And then somehow when you have two even level vertices, right? Now you look at its neighbors using non matching edge. You grow your tree, and somehow you realize that a neighbor of this vertex, even level vertex, is another even level vertex. Then you find the blossom. Okay. In this case, you contract the blossom, and you get a new graph, and you continue your algorithm with this new contracted graph. That is how it works. Okay. Now, what is the complexity of this algorithm? So what you need to realize is that each contraction operation reduces the number of vertices by at least one, okay, or even two. So the total number of contractions is bounded by the number of vertices. Okay. And what remains is the following. So for each graph, if it's bipartite, or I mean, so the you can find an augmenting path in order of e time. So you again you contract and you find on exposed vertex and you grow your search. Then while you are growing your search, you have three outcomes. One is uh, okay, you might find an augmenting path, or you find a blossom. If none of these cases occurs, then it means that no augmenting path. And these are done by enumerating your edges. So you run into either of these three cases in order of E iterations. Okay. And we know that the total number of augmenting path is also bounded above by the number of vertices. That's what we've also proved. So if you combine all these things, the complexity of Edmonds' algorithm is bounded above by v squared times c. The reason is that we have v contracted graphs, and the alternating tree procedure, the augmenting path algorithm, takes order of v times e iterations, and we are working on Edmonds v graphs. For each graph, it takes order of v times e to grow your tree and find the augmenting path. So if you multiply these two numbers, you get this complexity. Okay. And this is a naive bound on the complexity. You could and that's it. You can improve the complexity by something, yes, maybe using a better data structure. But this is a crude bound, proving that the algorithm is polynomial time, runs in polynomial time. Okay. Any question? Okay. Any questions so far throughout this course? We talked about, just to summarize what we've done, we talked about bipartite matching, and we learned augmenting path algorithm and the alternating tree structure that works really nice for bipartite graphs. But even for this non-bipartite case, if you just kind of be a little bit careful about a knot cycle, but there we have a way of dealing with it. You just contract the vertices and run the same algorithm, then that gives you what we want. Okay. Uh, okay. Yeah. Right. So, uh, right. I think the common perception, the folklore is that if you have a specific graph-based algorithm, even though the problem admits a linear programming formulation, I guess the graph-based algorithm is much faster than solving a linear program. That is the common perception, I think. Uh, so the question was about we have all this LP-based approach. If you solve an LP, you get a solution. Maybe we can somehow apply a rounding procedure, or maybe the solving this LP gives you on what you want directly. Now you compare that approach with this graph-based algorithm. Which one is faster? And many people say experience. I guess Professor Byung-In Kim has more experience than on this topic than me, uh, but uh, but I think Berchimas was one of the proponents saying, well, I guess the maybe it might be dangerous to say this on behalf of him, but I had a so listening to his talk, um, I had a feeling that um, the software like Groby and Simplex, they are so fast that even for some graph problems, if you have a nice little linear programming formulation and you run your software, because the software is so advanced that somehow, for some instances, solving a linear program or integer program uh, is much faster than a graph algorithm for some cases. Uh, so what I'm saying is the traditional belief is that graph algorithm is a lot much faster, but for some problems, maybe solving a linear program gives you something faster. Does this just answer your question? Okay. Actual running time. Well, in terms of time complexity, of course, LP, a linear program, there's no strongly polynomial time algorithm for linear programming, but LP for most graph problems, there's a strongly polynomial time algorithm. Are you aware of the difference between the weakly polynomial and strongly polynomial? Okay, it's a big open question whether there's a strongly polynomial time algorithm for an LP. Okay, but it's not known yet. But I was talking about the actual solution time. Okay. Any other question? Okay. In fact, the question is related to the second part of today's topic and the next lecture. In fact, there's an LP-based. So we have already talked about an LP-based approach for solving a bipartite matching or finding a maximum weight bipartite matching in a bipartite graph. But in fact, even for a non-bipartite graph, there's an LP-based algorithm. Okay. But it's not as simple as the bipartite case where we can just solve an LP and round the solution. We don't have such a something as simple as that, but there's an LP-based approach for even for non-bipartite matching. That's what we're gonna explore. And in fact, to discuss that, we need to define, talk a little bit about polyhedral theory. Okay? That's so let's step back from all these combinatorial discrete arguments, and I'm gonna discuss something a bit more about continuous problems. Okay. So let me talk about convex sets. Okay. Maybe many of you are already aware of this. So I'm given a set in the d-dimensional space. I say that the set is convex if for any two points in the set, its convex combination belongs to the set. What is the convex combination? Well, you take on weight between this 0 and interval, and you take this some point between u and v. So u and v, you take then this. If you take this combination, it will be located on this line segment between u and v. In this picture, the set on the left is convex because if you take any 2 points, the line segment joining these two is fully contained in the original set. But the set on the right is not convex because if you take these 2 points, you draw a line between them, this middle region is not part of the set. So this the second set is not convex. Okay. A convex combination. So we have, let's say, a finite number of points, v1 through vk. A convex combination of these points is defined as follows. So you take any linear combination, and we say that this linear combination is a convex combination if it satisfies the following properties. So the weight sum, coefficient sum is 1, and they are non-negative. Okay. That's what it is. Okay. So so linear algebra is quite important when you want to do research or if you will continue study on this. And apparently, I was talking to some other student and they were saying this. So I guess it was a linear programming course offered at POSTECH, and the professor was asking a question like, "What is a basis? What is a basis?" And apparently, the student didn't know what it is, and let's say you have some two vectors, and how do you determine that they are linearly independent? And uh, and the answer of the student was this: can you use the simplex method? I thought it was too funny, but I guess it was a non-answer to the question. So I was a bit amazed by that situation. So linear algebra is very important. So if you want to kind of continue study on optimization, I guess. Yeah. Anyways, okay. Sorry. Um, okay. So this is convex set and convex combination, and linear combination is also related to linear algebra. So so we need to define this notion of the convex hull. So what is it? So you have a set X, and the convex hull is you just collect all possible convex combination of points in there. Okay, then it's the smallest convex set containing this original one. And by definition, it can be written as follows. So now let's look at these examples. So let's say I have some discrete points, and if you take the convex hull, it's a pentagon containing those points as vertices. Okay, and also you can take this non-convex set, and now if you take the convex hull, you can make this set convex by filling up this region that were not there before. Okay, so this is kind of important. Well, I mean, why do we care about the convex hull? I'll explain it later. But let's say I have my the set of feasible solutions is not convex like this, discrete or non-convex, then you can turn it into a convex problem by taking the convex solve. That is the intuition behind it. Okay, great. So a related concept is this notion of polyhedra. Let me define what it is. So a set in the d-dimensional space is a polyhedron if it's defined by a finite number of linear inequalities. Now, if you look, okay, this is another point where you need to be familiar with linear algebra. I have this matrix inequality. So AX is a vector and B is a vector. It just means that if you expand this expression, you have let's say the rows of A are A1 transpose all the way up to AK transpose. X is at most B1, BK. This holds if and only if AI transpose X at most BI. So each row of this matrix inequality gives you something called a half space. So you draw a hyperplane, and if you take the set of solutions satisfying a single inequality, you take this bottom half. Maybe for another linear inequality, you take one half. And so these are called half spaces. Again, as the name suggests, you draw a half space which divides the entire space, and you take one of these two divided regions. Okay, and if you impose all these linear inequalities at the same time, then you basically take the intersection of these half spaces. Now you get this triangle in this example. Okay, this is called a polyhedron, and a polyhedron is called rational. Okay, if the data or the entries in this defining linear system are all rational numbers. You need to be careful about rational numbers because, well, I guess, computers cannot take irrational numbers, and we are working we're going to work on integer solutions satisfying a linear system of inequalities. Okay, but if your starting system is not rational, then the integer point inside this polyhedron could be quite funky. So you need to be careful about rationality, but you don't have to remember that at this point. So let's say we have a rational polyhedron, and a polytope is nothing but a polyhedron that is bounded. Okay, so if you have an unbounded direction inside your polyhedron, it's not a polytope. But if you don't have a kind of unbounded direction, then it's called polytope. And there's a nice little theorem for polytopes, and in fact, there's a version for unbounded polyhedron. But let's say your set is a polytope, if and only if you can find a finite number of points whose convex hull gives you the polytope. And the proof can be complex, but the intuition is kind of simple. If you have a polyhedron, because it's defined by a finite number of inequalities, you should be able to find a finite number of vertices like this: V1, V2, V3, V4, V5. And taking the convex hull of this discrete set of points, you get back to the original polyhedron. So this is the Minkowski-Weyl theorem. Okay. All right. Great. Now we talked about linear programming formulation or integer linear programming formulation for matching problems. But in general, a mixed integer linear program, or which is abbreviated as MIP or MILP, has this optimization form. So you have objective function that's linear in your decision variables, and you have constraints that can be represented by linear inequalities. So I have these matrices A, G, and vector B, just to collect all multiple linear constraints in my system. And maybe some variables are integer valued. Okay. So far we talked about the case where variables are binary valued, like 0 or 1. You can potentially take like 0, 1, 2, 3, and so forth. Okay. And you can also have continuous variables y. Okay. You say that, so if your so this optimization problem has both integer parts and continuous parts, then they are called mixed, because mixed in the sense that you both have a mixture of discrete and continuous variables. Okay. And in general, you can just simply say, oh, this is an integer program, and okay. Now, if you remember the matching problem, we have this binary valued variables. And what we've done was we replaced this binary constraint by non-negativity. Okay, and we call it as an LP relaxation of the matching formulation. So in fact, if you replace this integer valued constraint for x by x to the d, now all variables become continuous, and in that case, it's called linear programming relaxation, or LP relaxation of this integer program. Okay. And the feasible region, or the solution set of the problem, is just the set of vectors that satisfy the integer constraints and the set of linear inequalities. And then you just denote this set by S. Okay. And in fact, some set of the form is called a mixed integer linear set. Okay, it can be coming from the solution set of some mixed integer linear program, or it doesn't have to be. So any set of the form like this, where some variables are constrained to be integer valued, and there are some linear inequalities, then it's called a mixed integer linear set. Okay. Now, if you take the LP relaxation of the original integer program, then we just take out the integer constraint, and this thing is polyhedron, right? Because this is defined by a set of linear inequalities. And if the data or the entries of these matrices are rational, then it's called a rational polyhedron. Furthermore, if it's bounded, then we say that it's a polytope, right? Okay. Now for a mixed integer linear program, we have this feasible region. Again, these are something like you have a polyhedron, and it collects some discrete points inside this polyhedron. And now what I want to do is to look at this convex hull of these points. The reason is that, AX plus GY and mod B defines this purple polyhedron, but which can be potentially the actual solutions satisfying the integer constraints can be hidden inside this purple polyhedron. And I want to reach the point inside. That's why I'm taking the convex hull of the point inside, which gives you a smaller convex set. And it's known that, if the starting linear system is rational, then taking the convex hull of the point inside is also another rational polyhedron. Okay. What it means is that you need only finitely many linear inequalities to take the convex hull. Okay. This is not an obvious fact. Any questions? Okay. So the last part of today's lecture is this following lemma. Uh, this shows that you can reduce any mixed integer linear program to a linear programming problem. So what does this say? Well, let's say I have a linear objective and linear constraints and some integer constraints on some part of the variables. So that's written as the set S. In fact, even after taking the convex hull of this mixed integer linear set, you get the same value. Okay. Well, S is non-convex, but this becomes convex. So I'm making the solution space convex. That's what I'm doing. Okay. So another thing is that if you have a max optimal solution achieving the maximum value, then uh, then we the same conclusion holds for the convex hull as well. And here just to remind you or explain what it means. So this is defined by ax plus gy mos b, and x is integer valued. But this thing is another system, but with potentially different set of inequalities, g prime y and mos b prime. But now x is rd and y is rp. Okay. So you have a mixed integer linear program, and it proves that there must exist the same linear program by solving which you get the same solution. And then if you get back to the matching problem, well, for the bipartite matching, we got the same linear system, except we can just simply remove the integer constraints for bipartite matching, and also for stable matching in a bipartite graph. We keep the same linear inequalities and solve an LP. Well, what I'm saying is, what this lemma is saying, that for any integer linear program with potentially different system of inequalities, there's an equivalent linear program. Any question? Let's argue this. Let's prove this together. So first of all, max C transpose X plus H transpose Y, X comma Y in S. So the convex hull is a superset of this set S. So this is at most max C transpose X plus H transpose Y. XY belongs to the convex hull. Okay. Now this is straightforward because again the convex hull is a superset of the original set. Now I want to say prove that this thing is at least the right hand side. Okay, that's the real part. So all right. Okay, let's denote the value of the left hand side by G star. Okay. Then I'm gonna define a half space H given by a set of continuous points Rd times Rp. such that C transpose X plus H transpose Y at most G star. Okay, so G star, let's say this is a finite value. Well, if G star was not finite, then the right-hand side is also not finite. So they were pretty much the same. Okay. So let me assume that G star is finite. Then you can define a hyperplane or the half space like this using this inequality. What we know is that S is contained in H. This is by the definition of G star. So why is that? Well, G star is the maximum possible value of C transpose X plus H transpose Y. Okay, and we collected all points whose objective value is at most G star. Okay, and we know that this is convex. So if you draw a picture, something like this, H is half space, and S is perhaps some non-convex set that are contained in H. And now if you take the convex hull, it's still contained below this half space. You take any convex combination of points will also be contained in this half space. So because H is convex, it implies that convex hull of S is contained in H. What does that mean? Well, any point in convex hull of S is contained in H, meaning their values is at most G star. So that proves that G star is at least max C transpose X plus H transpose Y, XY in the convex hull. Okay. Now the question is about existence of an optimal solution, right? So I guess some student, I guess you asked a question about solving a linear program, and we talked about the existence of multiple solutions when you solve a linear program, and we somehow get a point in the middle of these 2 points, and it's related to that. So let me so suppose that suppose that X bar, Y bar is an optimal solution to this mixed integer linear program. Then X bar and Y bar also belongs to the convex hull of S. Okay, we saw that, because S is part of the convex hull. And when we argue that, this problem has the same value as the optimization over the convex hull. So then, hence, X bar, Y bar is an optimal solution to max C transpose X plus H transpose Y, where X, Y has to be coming from the convex hull. This part is easy. What about the other part? So let's say I solve a linear program given by the convex hull. Okay. And I want to find an optimal solution from the mixed integer linear program. Okay. This is the harder direction. Then because this x bar, y bar is optimal solution and which is coming from the convex hull is equal to a convex combination of some points lambda I, xi, yi, where first of all this is the convex combination and x1, y1, xk, yk belong to the set S. Okay. We're going to argue that all these points are optimal solutions to the integer program. We've done this argument when we analyze the bipartite matching formulation. We solve an LP, okay, and we got a solution, and we perturb their values, and then we prove that the LP solution is in the middle of these two perturbed points. And if you head on optimal solution to the LP, then the perturbed points are also optimal. Okay. And then we take one point and we perturb their points by breaking cycles and trees. And we saw that they are also optimal as well. We repeated this argument. Okay, we're gonna do this. So, great. So we know that C transpose X bar plus H transpose Y bar is at least C transpose Xi plus H transpose Yi for all I. Because X bar, Y bar is an optimal solution. Okay. But because of this relation, we know that C transpose X bar plus H transpose Y bar is equal to summation of I from K lambda I times C transpose Xi plus H transpose Yi. Well, we proved that, lambda i's are non-negative. And C transpose Xi and H transpose Yi is at most this value. So we get that this is I from 1 to K lambda I times C transpose X bar plus H transpose Y bar. We have the same thing for all i's, and the summation of lambda I is 1. This is equal to C transpose X bar plus H transpose Y bar. We got the same values on the left-hand side and the right-hand side, so the inequalities have to hold throughout with equality. So it means that this thing has to be equality. Let me prove that. Can we show? Has to be equality. Also, this has to be equality. It means that all solutions that give a convex combination, that gives this point as a convex combination are all optimal. Okay, this is what it means. Any question? Let me stop here and we meet again in 15 minutes.